start with the simplest thing you can tolerate and then gradually add detail, you can say, all right, I got this much more accurate, but it cost me much more simulation time. But I don't need that effect for every single test. You might have a part in there that weighs 1 nanogram, something that's incredibly light, something that's completely non-physical, something that couldn't ever be built. In a perfect world, you'd automate everything. Wherever possible, try to automate what you're doing, because I guarantee you'll get an answer now, but someone's going to come to you with a small change. You're going to have to do that whole thing again. If you wait till the very end to find, oh, let's see if our designs all work, it's typically a bad thing to happen.
Today we have a very special guest on the show. We'll talk about simulating the real world. And Steve is an expert in multibody dynamics and system modeling with Simscape. So Steve, welcome to the show.
Great. Thanks, Yusuf. It's really good to be here.
Thank you so much for doing this. Before we jump into the nitty-gritty, can you give us kind of a short introduction about yourself, Steve? What is your background and what are you working on at MathWorks?
Sure, I'd love to. So my name's Steve Miller. I work at MathWorks as a product manager for the Simscape product family, and that's for modeling physical systems of all kinds, mechanical, electrical, hydraulic, you name it. My background is mechanical engineering, and I've been at MathWorks now for about 20 years. But before I came to MathWorks, I did on-site simulation support at a number of car manufacturers. That's really where my background is. And prior to that, I did algorithm development for anti-lock braking systems.
Sounds super fancy. I think a lot of listeners somehow understand the term multibody dynamics, but what is it actually, and how is it used in engineering applications?
It's a good question. It's funny, the name multibody dynamics has all the pieces into it, but it's kind of a foreign term if you haven't heard it before. I mean, you can imagine multi means more than one, and body, those refer to mechanical parts that you find in pretty much anything that's mechanical. And so the term for multibody dynamics is used to describe systems with multiple parts that are typically connected by joints, so pins that allow things to rotate or slides that allow things to move back and forth. And the good thing about it is, like if you're trying to define something in physics using math, my daughters are in physics classes right now, and they're always coming to me for help. They're trying to derive equations for just a point moving through space. And that's not too hard. You can get that done on a couple of lines. But as soon as you have a pendulum, a double pendulum, triple pendulum, 4-bar linkage, and you start to describe all of that physics using equation, it gets really tricky. So multibody dynamics is an approach that allows you to describe the physics of these mechanical systems using a higher level language. Instead of going all the way down to the equations, you simply describe the parts, how they're connected together, how they can move with respect to one another, and then the multibody dynamics formulation will formulate the equations for you automatically.
I see. Yeah. What are some important parameters when defining multibody systems? For example, the stiffness of the part, how many parts there are, how long they are, etc. Like, what are some of the most important parameters? But at the same time, I mean, all molds are wrong, but some are useful, as we know. So how much of a trivialization is multibody dynamics, and what do we have to take into account when building these systems or digitalizing them?
Yeah, I mean, some systems you model are so simple that when you take the answer you get from the simulation, you compare it to real life, it'll match exactly. But the more complicated it gets, well, you're going to be a little bit further off, and it's going to take a bit of engineering judgment to figure out what effects am I neglecting, and then trying to add those in as best you can. I mean, key parameters are typically the sizes of the parts, so how long they are, where the pins are located or where the joints are located. And that information alone will get you a kinematic simulation, just telling you how far parts will move as they're being exercised through their range of motion. And then the part that makes it complicated is often the stuff you can't see or can't see easily. So when you're running these simulations, or even in the real world, nothing will just travel forever unless it's in outer space. There's going to be friction of various forms, like something rubbing on the floor, or even just air. Something going through the air will eventually be slowed down due to the aerodynamics. And so those are the types of things that are harder not only to model, but also even to remember that they're there. We're working with a university right now who's trying to measure the inertia of the chassis of a vehicle, and they have it rigged up on a pendulum to go back and forth. And the tests that they've done, they're not getting the answers they expect, and they know there are sources of friction in here that we don't really have captured, and we're going to have to figure out a way to estimate those because there isn't really a direct way to measure them.
Mhm. You earlier mentioned that your daughter is in physics, or your kids are in physics class. Now you're describing kind of the point mass systems. Now, when you go to multibody dynamics and trying to come closer to the real world, what equations are we working with generally?
I mean, there's Newton's laws. Those are typically the ones we use for dynamic equations. And then a lot of the stuff for pure kinematics is just sort of sine and cosine, sort of just angular relationships. And in those cases, you won't really need to worry about mass or inertia. But again, the more interesting, or not more interesting, but comprehensive analysis of a mechanical system will include both things. So pure kinematic equations that describe motion, and then Newton's laws to describe how things react to forces and move around.
I see. Yeah. How does MathWorks then connect to simulations involving multibody dynamics? How does that work?
So MathWorks is known for MATLAB, which is used for doing all kinds of mathematical calculations and plotting things. But there are ways to describe these multibody systems or these mechanical systems with a higher level language. So you can perform multibody dynamics directly within MathWorks products by defining parts, connecting them with joints, importing CAD models to define that mechanical system, and then running transient simulations to see how the systems will perform. One of the products that I am responsible for is Simscape Multibody, and as the name describes, it's for simulating multibody systems. But beyond that, typically a mechanical system, almost every mechanical system will connect to things that aren't purely mechanical. They'll be connected to motors that need to move things, or hydraulic systems, the cylinders that need to extend or contract. And so the good thing about simulating that within MathWorks product chain is you're able to connect that mechanical multibody system to other systems that are part of the overall design, hydraulic, electric, as well as control systems and software.
How does it work from an interface perspective? Let's say you have a hydraulic system and an electrical system. How easy is it to merge them inside of MATLAB or other tools?
Mm-hmm. In general, I mean, within the products that I work with, there, it's quite easy. I mean, typically, it's not so much creating the connection that's hard, because you pretty much connect things together in a schematic. So as long as you know what the 2 points out of the cylinder attaches to and how it's connected to the valves and the pumps, you pretty much connect it all together in a schematic. It's kind of like drawing a free body diagram or an electrical schematic on a piece of paper. So connecting the blocks together, that's not hard. What's important, though, is that you know first enough about your system to know where things are connected. Because if it's a system, what's common is, if, let's say I'm a controls engineer, I didn't design this system, but I need a model of the physical system to test the controller. Typically, that's one of the things where it's a little challenging, is you might need to speak to a designer to understand what's connected to what. And the other part that's challenging is starting to try and figure out, again, those parameters or those physical effects that you're not sure of. And even just deciding, do I need to include that effect or not? That's typically where the challenge is. The simulation tools will make many things easy to model. The trick is figuring out, what do I need to model and what can I neglect so that the simulation runs quickly and just gives me the answer I'm looking for.
Yeah, that makes sense. I mean, you've probably worked on a ton of use cases already, dozens and dozens of use cases. The question that comes to mind right now is, how do I know what to neglect and what not to neglect? I mean, you start from first principles, but then the question is, how far do I want to go? Like, is there kind of a system, like a rule of thumb that you personally use of what to model and what not to model? Or is it more like a gut feeling thing?
Yeah, that's a good question. What I try to do and what I advise other engineers to do is start with the simplest thing you can tolerate. Go as simple as you possibly can, and then gradually add detail, because that way you'll get if you compare the model the adjustment you just made to the thing you had before that, you can say, all right, I got this much more accurate, but it cost me this much more simulation time. And then you have you can sort of decide it's worth it. I'm willing to let it run for an extra hour to get that extra, whatever, 5%, 10% of accuracy. And if you're careful, you can also choose to back it off. So you say, all right, well, I added this very complex flexible body or contacts or whatever, and it made my simulation take, 2 or 3 times as long. But I don't need that effect for every single test. So if you're careful, you could take the model and adjust it to have the effects that you need when you need them, and then turn them off when you don't.
Yeah, that makes sense. What are some of the use cases that you have personally worked on, which have been hard, but maybe also, I'm not sure if you can say easy in multibody dynamics, but maybe some of the ones that are less complicated, more complicated?
Sure, yeah. When I was doing on-site support, typically I got all the models that were broken, or it was a model that someone worked on and then they left the company. And those were challenging and complicated. And oftentimes I didn't have anybody I could ask, like, how did you do this? Why did you do it this way? So a lot of times I had to take those models and break them all the way down to modular pieces and make sure that each part was working correctly or each interaction was correct before assembling the whole thing together. I mean, I remember I spent a lot of time on steering systems, like power steering systems. And typically the ones I was working on, there was the steering wheel, which would turn, and then there would be a portion of the shaft that would twist, and that twist would be information for a motor that would apply a torque to help the driver steer the car. And a lot of times, a lot of these power steering models, like the motor model, it was suitable for another task, but not for a power steering model. So I had to take the motor model, connect it to just a couple of shafts, and make sure that it was suitable for the model that we had. It had the right physical effects. It was going to simulate quickly. It made, it applied torque to both shafts and not just one, because some people would skip that kind of stuff. And then I would gradually build up the rest of the power steering system so that at the end, you could see on the screen a steering wheel that was turning. You could see that the wheels were steering. And you could also measure how much torque it took for the driver to apply to get that whole thing to steer. That's a fairly, in automotive cases, that's a typical one. I also spent a lot of time modeling suspensions, like car suspensions, which have many linkages, and so mechanical parts that connect the wheel carrier and the tire to the chassis. And sometimes those connections were rigid. Sometimes they were flexible if they were bushings. And so, but in all these cases, it was a matter of what question is the model trying to answer? What do I need to answer that question? And then just making sure that the foundation of the model was solid, that there weren't any mistakes hiding in there that were going to corrupt the result.
Yeah. What do you think from a physical perspective are some of the more challenging things to implement? Is it something like which is just nonlinear from nature, like such as contact that you just mentioned, or something else as well?
Typically the things that are hardest to implement are effects that you have to use a bit of engineering judgment or approximations or just sort of correlated models or equations to create an abstract version of something that's very difficult to represent physically. There's a lot of tools out there that are targeted for there are specialized tools out there that they're designed to go as close to the physics of the interaction as possible, like computational fluid dynamics or FEA. And those are trying to get as close to the physics as you can. But some of those simulations will take days or weeks. We even have engineers we work with that have simulations that run for months. And so that's not where we're typically, not what we're aiming for if we're trying to look at an entire multi-body system. So the challenging part is, again, like as you mentioned, so anything that's nonlinear, to make sure that you understand which equation is going to match the physical behavior. And then also just knowing like how abstract can I make this and still get a good answer? And then once you have that abstract formulation that simulates quickly and looks like it's going to capture the behavior of the real system, how do I tune these abstract parameters? They may not have, they may just be points in a lookup table or coefficients in a polynomial or something like that. It may not be easy to figure out how those values match up with the real world. And so that there's a bit of an art to that as well, to make sure that you tune these abstract laws so that it contributes the correct nonlinear force or what have you to the multi-body system.
How do you then debug these systems? That would be interesting to understand, because let's say you run into an error. I'm not sure how an error in Simscape would look. I guess it may be like a convergence issue. And how do you actually then debug these systems?
That's a good one. I mean, there are so many different ways that a simulation can give you an answer or result in a state that's unexpected. You typically need to have a lot of different ways of looking at the problem or looking at the model or looking at the results in order to home in on what the true solution is. Typically, if you run a simulation and it stops, it'll give you some form of a diagnostic saying, these equations couldn't converge. And a lot of times the problem there is, many times the problem there is what you put in there isn't really physically realistic. So you might have a part in there that weighs 1 nanogram, something that's incredibly light, and you've got it attached to an extremely stiff spring. So then you've got, a system that's going to be having massive accelerations. And in those cases, it's likely you might have just put it in there, you didn't set the density properly. And so you've got something that's completely non-physical, something that couldn't ever be built. And so a lot of times as far as the debugging process is concerned, when the simulation stops, hopefully there's a diagnostic that points to which part is accelerating too quickly, spinning too fast, and can you see at what point that was triggered? That will hopefully let you home in on the part, the degree of freedom, or the force law that's contributing to this non-physical behavior, and then start to fix things from there.
That makes sense. You've mentioned, I think most of the examples were from the automotive space. Any other industries where you were working on in terms of multibody dynamics, some other applications?
Yeah, I started in the automotive industry, and even automotive industry has things that don't, and you think of cars and wheels and things, but they're also like power roof on a convertible. It's essentially just a linkage, and you can find those in all kinds of different systems. For example, in robotics. So there's lots of robotics systems out there, and multi-body simulation is very heavily used there. I work with a course at the Technical University of Munich, and we do a lot with robotics there. Not only things that grab and pick things up like you might see on a production line, but also robots that drive around on the ground to find things or carry something from one place to another, and even walking robots that have to climb over obstacles to try and find a human who might need something, or scanning a construction site to see what has changed in the past 24 hours. These are all that's sort of an area of robotics, a number of different applications. I've also spent some time working on construction equipment. So tractors in an agricultural area, backhoes, motor graders that make roads, that make things flat. That's another place where multi-body simulation is heavily used, and where I'm active with a lot of engineers working on those systems.
That's super interesting. I'm wondering, how has multi-body dynamics changed during your career? Because I think, first of all, first principles don't change, right? From a solver perspective, new insights maybe into multi-body dynamics, modeling approaches, any insights there? How things have changed over the last couple of years?
Yeah, I've been working on multi-body simulation now. It's kind of scary, for more than 20 years, probably getting close to 30. And when I think back to the problems that I was working on in the beginning, they were all almost purely mechanical. Like the power steering example I mentioned before, there was a motor in there, but it wasn't really electrical. It had some very simple equation to describe how the current and voltage contributed to a torque. So anything that was in another domain besides multibody, it was all handled extremely abstractly. And that was because there were a lot of very specialized tools for solving specialized problems, be it mechanical, hydraulic, what have you. But when I think about working on-site at auto manufacturers, then coming to MathWorks and working with a wide range of customers, one big thing that's changed is that now these problems that you would have separate teams and separate engineers working on with their own specialized tools, and they just kind of, throw an answer to the other team. They're now trying very hard to integrate those different designs, the mechanical, electrical, hydraulic, what have you, to make sure that there isn't a surprise when you put the whole system together. Especially in like large complex systems, if you wait till the very end to find, let's see if our designs all work, it's typically a bad thing to happen. We've worked with some companies that work on excavators, and the first time that a lot of these designs will come together is at the very end. Well, not the very end, but the first time they're together, what's called a mule, like a prototype, where they've got kind of cobbled together mechanical parts and then the hydraulic system from the last design, and they put it all together, and it's like, this thing can't lift it. It's not powerful enough. And then, teams are pointing at each other. They say, well, the hydraulics aren't strong enough. Well, you put the pit in the wrong location. This was common when I started working with multi-body simulation. And now, certainly over time, I've seen these types of problems can be investigated earlier and earlier in using simulation, because you can truly combine the multi-body mechanical stuff with hydraulics, electric motors, batteries, that kind of thing, and pull it again, check that kind of stuff early on, rather than investigating in separate specialized tools and then just, crossing your fingers that when we put it all out in the field that it works.
Yeah, what do you think, going back to that point, what kind of design decisions would require an engineer to understand what to integrate? So if it's like an electrical system, hydraulic system, or other systems into the simulation, when is the right time to do so?
I mean, typically by default answer is as early as possible, because the earlier that you start investigating how the different parts of the design interact with each other, the sooner you can start eliminating portions of the design space that don't make sense, or eliminating like coming up with starting to refine the requirements for the different parts of the system. I mean, even in a pure mechanical simulation, you can figure out, well, how much torque is it going to take to turn this wheel? How much force is it going to take to extend this cylinder and move the boom out on the excavator? Even if the model doesn't have any hydraulics in it, the mechanical engineer is giving useful information to the hydraulics engineer to say, hey, if I put the pin here where we put it last time, I'm going to need this much force. So whatever you do with the pumps and the valves and the actuator, if you can't produce this much force, I'm going to have to redesign the mechanical part. It also works the other way around, is that the hydraulic guy could say, all right, if you're going to put the pin there, and if I'm going to have to supply this much force, the only space I've got for this, I'm going to need this much area for the piston. So I need this much space for my cylinder. So if you're going to change your part of the design, it's going to affect me. And so that sort of interaction is one. I mean, on the other side, that's more about like how much force or how much torque something provides. Another way of looking at this is how much energy things will require to run over a long period of time. In the area, like sticking with construction equipment, key metric of performance is how long can I be out there digging before I run out of fuel or before the battery runs all the way down. And you can, in a simulation, sort of check and see how much energy does it require to do one dig cycle. Okay, now let's extrapolate that over an entire site. Will I be able to run half the day, all the day? What's going to affect that? So these are some of the questions that engineers will be looking at sort of very early in design, as early as possible. Like, please help me figure out, which portion of the design space to look for, what size of actuator is appropriate. And then also, as you move down through the design process, okay, how long can we run this thing? Do we have something that's going to be able to compete with other machines on the market?
Yeah, how does the tool specifically help engineers in that regard? Because as we all know from the simulation space, if you front load, for example, the kind of the product development process using, for example, CFD, it's much easier to understand the real world behavior using kind of a surrogate model, so to speak. Mm-hmm. So how does, in terms of multibody dynamics, how does simulation help us as engineers to kind of make decisions very early in the design stage? I mean,
a multibody model can answer all kinds of questions. And so pretty much regardless of what stage you're at, there's questions it can answer. A common thing is for vehicles is how heavy is it going to be? And so how heavy it's going to be is going to be affected by where are the parts located, how strong do they have to be, how much motion do they have to have. And so once as you start to refine the design and simulation, that will allow you to refine what the design will look like and start to answer some of those questions early on that you would need to know. But again, even the whole way through, there'll be points in the development process where there's a design change because there's a new requirement. We have to climb a 30% grade at a certain speed for a certain amount of time. It's like, oh, we didn't have that requirement before, or a competitor just came out with a product that can do that. All right, we need to go back to the multibody simulation and see what's it going to take to climb this grade and be stable as we go through curves, for example, to make sure that we have a product that will be competitive when it comes out on the market.
Yeah. How does an engineer or an engineering department know what to focus on when building these systems? Is that kind of a trick that people can use, or engineers in this case?
Trick. Yeah. I mean, I'm sure the people that have those tricks are probably very well valued. I mean, a lot of times most of the engineers that I've worked with, they have a process is trying to figure out what do we do at each stage, and as we go through the development process, there'll be sort of checkpoints. By this time, we must know this with certain amount of certainty that we'll be able to execute these types of tests on the machine. The excavator with a dig cycle, for example, that's a standard one. Or in a car, it must be able to do a double lane change and stay within a certain deviation from the path. And I think as far as what to focus on, I think engineers early in the development process, you don't know as much about everything. So sort of I would say the key benefits you get at the beginning, again, as I mentioned before, is sort of eliminating portions of a design space that don't make any sense. Because the last thing you want to do is redesign the whole thing because you forgot something or you didn't check something that you knew about in the beginning. You know what I mean? Like, we know we're going to have to lift this much weight. That's a test you can run very early on, regardless of what the specifics of the hydraulic system are. And if you have a disciplined approach to sort of checking the critical factors as you go through, that's a way of avoiding redesigns and avoiding surprises down the road.
Yeah. How much of that kind of manual work can actually be automated inside of the environment, of the software environment?
I mean, in a perfect world, you'd automate everything. I mean, that's most of the time when the engineers that I work with, I advise them wherever possible, try to automate what you're doing, because I guarantee you'll get an answer now, but someone's going to come to you with a small change. You're going to have to do that whole thing again. So you want to automate. I always advise automating as much as possible. Almost anything can be automated if you have a good scripting language. I mean, I've written lots and lots of MATLAB code to automate parameter sweeps, for example. Like, again, early on in the process, I don't know where these pins are going to go or how long the suspension arm's going to be. Well, let's let the tool tell us, if it's this long, you get a good range of motion. If it's this short, you're going to get funny kinematics. And so that type of sweep can be easily automated if you have a parameter for the length or a parameter for the pin location. You can just have the tool run as many tests as you want. It can even be overnight, and you can just see all the results in the morning to see, did that make sense? In addition to running the tests, you can also use automation to post-process the results to see, you can get a report in the morning saying, here are the ones that passed and here are all the ones that failed. You could even, if you're even more advanced ways would be, okay, not just single parameters, but also just completely different designs. Like, I have a hydraulic option, an electrical option, and each of those have different variants as to which type of motor or which type of pump. You could also automate just testing all of those designs. Those could be testing designs that you have worked on for years, or testing new ideas that someone came up with, or a new supplier. Maybe you have a new supplier for pumps or arms. You could also just run a sweep you could automate the process of evaluating that new supplier.
Yeah. How relevant right now at this stage is AI assisted modeling, or AI in general, when it comes to multibody dynamics?
It's relevant. It's relevant, and it's becoming more relevant all the time. I think most customers I work with, if they're not doing something with AI, they feel like they should be. And a lot of times, if it's something they've never worked with before, it can sound foreign or unreachable, sort of high tech. You need specialists for that. But the simulation tools are offering more and more to make that accessible and help you leverage it in your daily work. There's an example that I worked on was to take an entire vehicle, the multibody dynamics of a vehicle, and run enough tests and do enough work with the results of those tests to create an AI surrogate model that could predict the behavior of the vehicle as it's going over a bump or going through a lane change or braking to a halt. And I'm not at all an AI expert. Fortunately, I work at a company where there are a few. But even then, with a few tips and a few pointers to which examples to look at in the documentation, the process is actually not quite so foreign. If you have something to lean on, you have an example to work from. And like I said, companies are looking to this more and more. One, because they know everybody else is doing it. But two, they do see the advantage. If I can identify a specific question, I can create a surrogate model that will answer that question very, very quickly. And then that can be used to accelerate exploring the design space and ruling out options that don't make any sense.
Yeah. Is there any case study you could publicly talk about when it comes to, so either do I choose a physics-based approach or do I choose a data-driven approach? Or maybe I can even merge these insights together and kind of find a more optimal operating point, for example.
I mean, the most recent one that I worked on was more of a data-driven approach. I mean, it was an AI model where we ran lots and lots of tests, varying 94 different parameters to check and see, to characterize how the system behaved. And then we took the results of those tests and we trained a bunch of different AI models, both physics-informed neural networks and other types, just to see which ones gave us the best accuracy. And that step was actually like preparing the model and running all the tests. That took a decent amount of time. Training the model was quite simple. That ran very quickly. And by working with this type of thing, we ended up with a model after following all the steps in the documentation. We had a model that predicted what the multibody model predicted, what gave as a result. The predictions were extremely close. And then now we have an AI model that can answer a question very fast. And so then now we can run all the iterations we want. We used it for optimization to try and tune the hard points in the suspension. And that, again, to try and do that on the multibody model would have worked, but it would have taken a lot longer. And we could use the AI model to say, all right, focus your analysis on this portion of the design space, moving this critical set of points in these ranges.
Yeah, maybe fast forward looking maybe 5 to 10 years into the future, how much do you think AI will play a role in multibody dynamics? Will there be more AI coming? Whatever AI means in this case.
Yeah, I mean, when I see the number of places that AI is being investigated, it's all over the place. As far as the example I described was using AI to to essentially replace the multibody model to answer a specific question. But we're also seeing AI being used. It's used in cases where there's something I have to model, and you know what? I don't really know the physics well enough. So I'm going to try, but I have lots and lots of data. So I can use the data to characterize that. And I've seen it used sort of at a higher level to simplify a characterization of the entire system, but also to give us a viable model for pieces within the system. So these nonlinear physics that I described earlier, that you can use, those are two places where AI is being used in just the modeling side of the house. And I can imagine that it'll be used in other steps along the way as well, characterizing parameters, even in post-processing to recognize whether you've come up with a design that's good or not.
Yeah, that makes sense. You mentioned the documentation, Steve. So I'm wondering, as, for example, simulation is being democratized, right, for quite some time right now. I know the term democratization has been misused a lot of times. But do you think, apart from mechanical engineers, also other types of engineers can use or like implement multibody systems?
For sure. I mean, that's, I would say part of it, I mean, the foundations of multibody dynamics were to let mechanical engineers describe more complex systems. And that sort of tool is useful not only to mechanical engineers, it also enables non-mechanical experts. Why I can look at that mechanism over there and see how it's connected. And the high-level language allows me to connect the pieces together in the same way. So that would allow a controls engineer or a hydraulics engineer to connect these things together to build their own multibody model. The other good thing is multibody experts who create these models, they not only create it for themselves so that they can answer a question, they can actually share these models with other types of engineers or even non-engineers so that they can benefit from the accuracy and the predictions that a multibody model can make, even though they may have no contact and no connection with simulation. There's, I've seen apps created where someone comes up to the app and they enter a few key parameters, like lengths or not even lengths. I need this mechanism to reach this far. Okay, please tell me what type of mechanism or how big the motor needs to be. I know nothing of simulation. All I know is I know what I want my system to do. And that's a way for the multibody expert to create something that benefits people that have no connection to simulation. They can benefit from those types of models.
That's really, really cool. Do you have, maybe to wrap it up, some actionable next steps for people who are listening to this episode? Kind of, maybe they want to delve into multibody dynamics, maybe play around with MATLAB or Simscape. What would you recommend them to do?
I mean, typically the best thing to do is just if you have any type of mechanical system that you're interested in, it can be as simple as sort of a top spinning on a table, or as complicated as, again, some of the construction equipment you might see on the street. If you just think about how those things work and what it might take to model them, and then you can try it. I mean, there's lots of resources for learning or taking first steps with multibody simulation, Simscape Multibody has an online self-paced tutorial that you can simply try. And it shows you how to connect parts together with joints and run simple simulations, and even start to take steps towards integrating actuators or contact with things touching the ground. So I would say if you're interested in simulating something like that, this self-paced tutorial, the Simscape Multibody on-ramp, is a great place to begin, because you can just try it in a browser. You don't even have to install anything. And that's a really good way to even just see, is this interesting for me? Is it something that can help me with my engineering tasks, or is it something that can help me in my job? I would say those are good places to go. The other good place to go for inspiration is just to see what other people have done. I mean, if you search in the internet, you'll find all kinds of animations. If you look for computer animations of multi-body systems with your favorite machine or mechanism, you'll find all kinds of things. And we have a place where people store and upload models. It's called the MATLAB Central File Exchange. I am always amazed at the things that people upload there. I found a satellite model just this past week with reaction wheels and flexible solar panels, and that was all connected to like signal processing as the satellite's sort of pointing itself towards different things with signals it's trying to capture. There's a lot of really interesting stuff out there. I would say those are two good places to go.
That's good stuff. We'll put all the relevant resources in the description of this video so people can actually check them out. And again, Steve, thank you so much. I learned certainly a lot about multibody dynamics. I only touched it maybe once or twice during my uni career. But yeah, thank you so much, Steve. I appreciate it a lot.
My pleasure. It was excellent to talk to you. Thanks.